picking up where we left off, we were just kind of setting up, again, this relationship of Kw is equal to the concentration of Ka, if I have one, and multiplied times the Kb value, which is a result of knowing these two values. And I can swing this around the other way as well. And again, we can also look at hydrogen ion concentration, hydroxide ion concentration equal to this value. These are sort of usually two different conversations, but we can just kind of keep that in the background for now. All right, so if we look at calculating the OH or hydrogen ion concentration or the hydroxide ion concentration, we have this little setup here. Now, just for example, what we were kind of fooling around with some of these problems over here, if I have the hydrogen ion concentration, there it is. If I want to make this a little more palatable, because it's the real value, that's how much it is, but I don't like it. Most people don't. We can actually just use this as a tool. There's not really a whole lot of magic. Why is negative? Just because. It makes it look a little nicer. So negative log of 1 times this concentration, and again, this is the hydrogen ion concentration, that will give me an answer of 7. So what's the pH value? It's 7. What does that refer to? It refers to the hydrogen ion concentration, which is 1 times 10 negative 7. They mean the same thing, exactly the same thing. This one's just a little more palatable than the other. And of course, if I know the pH concentration, pH plus pOH always equals 14. So if I know one, I know the other. It must be 7. There it is. That part's done. All right, let's do one of your homework problems, and we will swing back over to the notes once we get that done. For our first homework problem, number 17, designate the Bronsted-Lowry acid and the Bronsted-Lowry base on the left side of each of the following equations, and also designate the conjugates on the right side. So again, we're going to use the same method we used in the previous problem and look for something that is gaining or losing a hydrogen ion over on this side compared to the right side. So here I have NH with 4 hydrogens, and here it is with 3. So clearly this is acting as an acid. I'm just going to put A for acid here, and this therefore must be the base. Now, after an acid has donated its hydrogen, the result is going to be a conjugate base. And if this is a conjugate base, this must therefore be a conjugate acid. So really, once you get one of them down, the rest of them all fall into place. The next one here, looking at this, I'm looking for what's going on. Okay, I see N, now I see NH. So therefore, clearly this one has gained a hydrogen. So I'm going to write base here, and then therefore I can kind of see this pretty well. This is an acid, and then if this was a base, this must be a conjugate acid, and therefore this must be a conjugate base. All right, the last one on the list, with a hydrogen, without a hydrogen, must be an acid, donated a hydrogen. As a result, this must be a base. If this was an acid, this is now a conjugate base, the result. And then this therefore must be a conjugate acid. Problem done. Okay, let's swing back over to our notes. Next part, we're going to do kind of a little math problem here. We're going to calculate the pH of a strong base given the concentration of this, which is NaOH, is 0.028. And again, this is something we could just make up in the lab. A concentration of sodium hydroxide, here it is. We want to figure out what its pH would be in solution. So we do remember, just to kind of put some familiarity stuff around, if you add water to water, what you would actually get is hydronium and hydroxide ion. All right, well, fair enough. I know the concentration of one of these things here. The other one I don't seem to know. So I'm going to write down an equation that we have just a little bit above and say the hydronium or hydrogen concentration times the hydroxide ion concentration is equal to Kw. Kw is a constant. Do not forget that value is 1 times 10 to negative 14. I also know this value is right here. So remember, this separates up completely. Sodiums always separate. This goes to completion. Strong bases go to completion. So that value is true. Therefore, this is my hydroxide ion concentration. So I know that value. I know this value. And I need a pH. And these two guys are directly related. I know this is a lot. So let's just kind of play around with this and figure it out. If I have these two pieces of information and I'm going to isolate for this one here, what I can do is take this and divide it by this. So I'm going to write that out. 1 times 10 to the negative 14 divided by 0.028 is equal to 3.57 times 10 to the negative 13. Okay, so what is that equal to again? It is equal to the hydrogen ion or hydronium ion concentration, the exact same thing. Now, based upon what we were doing over here, I can place this value into here and get a pH value. So if I say negative log of 3.57 times 10 to the negative 13, I will get an answer of 12.45, which should look reasonable because, again, this is sodium hydroxide, which is basic, and this looks like a basic value. There you have it. Done. All right, let's swing over and do another homework problem, number 39. For number 39, the average pH of normal arterial blood is 7.4 pH. A normal body temperature is 37 Celsius. We have the Kw value. So this is the only problem we will do all year long that is not at 25 degrees Celsius. We're using human body temperature, 37 Celsius. So notice Kw is not 1 times 10 to the negative 14, it's something other, 2.4. It's a little bit higher. We want to calculate these concentrations and the pOH for blood at this very specific temperature. So we know what one is. The pH is 7.4, given that. We also know, as a result of this, the pOH is going to be 6.2. And the reason we know that is because of this value here. And I'll come back around for that in a second. First thing we're going to do is just take a look at the hydrogen ion concentration. If we do the opposite of what we were doing before the negative log, the opposite of that process is to take the E of it and a negative pH. So 10 raised to the negative pH value, and that pH value is again 7.4. So if we do the math on this, so second function on your calculator, and then E is this like e to the x, so E negative pH. What that'll give you is 3.98 times 10 to negative 8. And again, just to go back and tell you where this number comes from, if you put this in on your calculator using negative log of this value, you're going to end up getting 13.6. 13.6 will be the total value for that. So that's where this value actually comes from. So I kind of jumped ahead on that a little bit. This last one here, the OH, using the exact same process, is going to be 10 raised to the negative 6.2, and that's 6.31 times 10 to the negative 7. So that's the answer. And again, the one part I did leave out here is taking the negative log of this value here, and that'll give you the 13.6. Good enough. Okay, that's a good place to take a break for the end of this lecture.